Welcome to videos on Bode plot. So in this video we shall see how to plot the Bode plot for a few examples. So let us consider a transfer function having two poles having time constant 0.1 and 0.01 with a gain of 100. So the expression for the magnitude is given by this expression, and the phase is given by the second expression, that is minus tan inverse of 0.1 omega minus of tan inverse of 0.01 omega. The phase varies from 0 to minus 180 degree, and magnitude varies from initial 40 dB with a slope of 0 dB per decade, and there is a pole at 10 radian per second where the slope changes from 0 dB per decade to minus 20 per decade, and after 100 radian per second the slope changes from minus 20 dB per decade to minus 40 dB per decade. So let us start plotting the Bode plot for this transfer function. So this is the Similog sheet where the magnitude plot of the Bode will be plotted. So on the x-axis we have the frequency in terms of radian per second. We are starting the frequency as 0.1 radian per second. Next it is 1 decade, which is 1 radian per second, and this is 10 radian per second. This is 100 radian per second. This is 1000 radian per second likewise. And we have taken the scale of this as 1 unit is equal to 20 dBs, taking this as the reference 0 dB line. So it is 20 dB, 40 dB, 60 dB, and it is below 0 dB. Now it is 1 unit is equal to minus 20 dB, minus 40, minus 60, and minus 80. So on this Similog sheet we'll be plotting the magnitude plot of the transfer function what we have considered. So let us start with the first term of this equation, that is 20 log of 100. Since 20 log of 100 is 40 dB, we are writing a line at 40 dB line. We know that the magnitude of this 100 will not change with the frequency. That's why it's a for any frequency starting from 0.1 to 100 kilohertz, 100 kilo radian per second, the magnitude contributed by term 100 is 40 dB. So that's why it's a straight horizontal line with a slope of 0 dB per decade, which is having a magnitude of 20 log 100, which happens to be 40 dB. So this is the first plot representing magnitude of 100. In terms of dB, it is now 20 log of 100. And let us consider the second term. So this is the first term corresponding to 20 log of 100. The second term is 1 over 1 plus 0.1 s. So we know that the contribution of this 1 over 1 plus 0.01 s starts from the cutoff frequency, that is 10 radian per second. So till 10 radian per second the magnitude contributed by this pole is actually 0 dB. So that's why its contribution is 0 dB. After 10 radian per second, the magnitude decreases with a slope of 20 dB per decade. Carefully observe here. Now from this point, that is at omega is equal to 10 radian per second. So this is 10 radian per second frequency. We are coming down by 20 dB, that is this point, and we are going 1 decade here, and this is this point. So we need to join this point and this point, and you can see this is a line corresponding to 20 dB per decade, that is minus 20 dB per decade. So minus stands for below that reference point. So from this we are coming down by 20 dB, which happens to be minus 20 dB per decade is. So from this point 20 dB down is minus 20 dB, and this is 1 decade. So this slope is minus 20 dB per decade. So this passes through this point and it is extended till the end. So this line now corresponds to 1 over 1 plus 0.1 s. Similarly, let us try to plot the magnitude plot for the third term, that is 1 over 1 plus 0.01 s. Now this is a representation of the second term, which is 1 over 1 plus 0.1 s. I can say this is the representation of the third term, which is having a cutoff frequency at 100 radian per second. You can see now the contribution due to this term, that is 1 over 1 plus 0.01 s, is 0 dB till 100 radian per second. You can see this is 100 radian per second. So its contribution is 0 dB. Afterwards, its contribution is minus 20 dB per decade. So now we need to draw this line with a slope of minus 20 dB per decade. For that we are coming down by 20 dB from this point of 100 radian per second. Now this is coming down at a frequency 100 radian per second, and it is 1 decade point. Now you can see this is 1 decade. Now we are joining this point and this point, which will give a slope of minus 20 dB per decade. The line corresponding from this 0 dB, so till 100 radian per second it is 0 dB, and the slope is also 0 dB per decade. And you can see now it is dropping with a slope of minus 20 dB per decade. Now we have all the three terms represented in the on the graph. So this is 100 corresponding to which this is the representation corresponding to this term. It is a 0 dB slope line, and it is minus 20 per decade after 10 radian per second. And this is the representation of the third one, that is till 100 radian per second it is 0 slope, and afterwards it is minus 20 dB per decade slope. Now in order to get the resultant slope, since it is logarithmic, we need to add all the plots, that is this plus this plus this. So initially from 0.1 radian per second to 10 radian per second, the magnitude contributed by this is 40 dB. The contribution of these two terms are actually 0 dB till 10 radian per second. So as we can see now in the resultant plot, it is 40 dB till 10 radian per second. Afterwards we know that this is contributing, the second term is contributing a slope of minus 20 dB per decade. Now you can see this is contributing minus 20 dB per decade. So when we add this plus this plus this, so from 40 dB point it comes down by 20 dB per decade till the next cutoff frequency. That's what is happening here. So this is a resultant slope, resultant plot. So this is 40 dB till 10 radian per second. Afterwards the influence of this term will start. So this will have a resultant slope, will have a resultant plot will have a slope of minus 20 dB per decade till the next cutoff frequency. The next cutoff frequency is at 100. I can see from here we are coming down by 20 dB, and this is 1 decade. We are joining this point and this point, which will give a slope of minus 20 dB per decade. After at 100 radian per second onwards, the contribution of this also starts. So we have the contribution after 100 radian per second due to this term, that is 100. We have the contribution due to this also, which is a minus 20 dB line, and we have the contribution of due to this also. So as you can see now, after 100 radian per second, the overall slope happens to be, just a minute, overall slope happens to be minus 40 dB per decade. So that's why you can see this slope is now changed from minus 20 dB per decade to minus 40 dB per decade. Then how to plot this minus 40 dB per decade is, from this 100 radian per second frequency, from this point you come down by 40 dB, that is minus 40 dB we are coming down, and then this is 1 decade. So we have one point here and the second point is here. If I join this and this point and extend till the end, the slope happens to be now minus 40 dB per decade from 100 radian per second onwards. Meaning to say, in the previous plot, as you can see now, so till this 10 radian per second the slope is 0. Between 10 and 100 the overall slope is minus 20, 0, 0. So it is minus 20. So after 100 radian per second the slope is 0 here. This is minus 20. This is another minus 20. So from 100 radian per second onwards, the overall slope is minus 40 dB per decade. So that's why we saw in the resultant plot, so till 10 it is 0 dB, between 10 and 100 it is minus 20 dB per decade, after 100 it is minus 40 dB per decade, because there are no more changes happening after 100 radian per second. You can see there are no change in the slope even after 100. So the slope is 0 here, this is minus 20, minus 20. The addition of the slope is minus 40 dB per decade after 100 radian per second. So that's what is happening here in the resultant plot. After 100 radian per second, the resultant plot is minus 40 dB per decade. So we know that this omega gc, which happens to be where does this magnitude plot crosses 0 dB. So this is actually 3 not 10. See now this is 100. This is 100, this is 200, this is 300. So this is somewhere close to 310 radian per second. So this is omega GC. Actually, in the earlier videos, we have actually found out omega GC from calculation using the equation. Omega GC was coming out to be 308.3 radian per second, and omega PC was infinity. Why this omega PC was infinity is because we have only two poles. The frequency at which the phase crosses 180 degree would be uh, infinite. So the corresponding omega phi of omega GC is minus 160 degree. We're going to have a phase margin of 20 degree and gain margin is uh, infinite dBs. Now system is stable here. So let us go back and see. Now you can see this is the resultant plot. Initially from 0 to 10 radian per second, no slope, that is 0 slope, and after 10 till 100 it is minus 20 dB per decade, then it is minus 40 dB per decade. So let us see this second example where we have three terms. There is a pole at 5 radian per second, there is a pole at uh, this is corresponding to 100, this is corresponding to 50. We have poles at 5, 25 and 100. So let us see what does the magnitude and the phase equations look like. Now this is the phase magnitude and phase equation. Let us start plotting the magnitude plot for this. The first plot corresponds to, because here we are writing the resultant plot directly. The first term is 20 log of 200, which happens to be 46 dB. So till 5 radian per second. So this is 0.05, 1 over 0.0, 1 over 1 plus 0.05 s corresponds to a pole at 5 radian per second. Till that point the slope is 0 dB per decade. So you can see this is actually 1, 2, 3, 4, 5. So till 5 the slope is 0. After 5 the slope happens to be minus 20 dB per decade. So let us see how do you find out that. So this is now 5. You come down by 20 dB, go by 1 decade, so which happens to be 50 now. If I join this point and this point, so the slope happens to be 20 dB per decade. Now we cannot join from this to this in total because the next cutoff frequency is there at 25. So we should extend this line only till 25. So let us not extend this till, okay, this is a dotted line taking this as 20 dB and 1 decade point. So this is actually 5 here. You are coming down by 20 dB. You are going to 50 because this is 1 decade. So this reference point will going to give a slope of 20 dB per decade, which is minus. So we have to extend this line till only the next cutoff frequency, which is at 25. So let us see in the next slide, it is stopping at 25. You can see now this has started from 5, its reference is next at 50, but we are stopping at 25 because this happens to be 10 here. Now this is now this line is 20, this line corresponds to 25. So after 25 the slope changes. We shall see what happens to the slope after 25 because our transfer function says that. So there is a pole at 25 here. So after 25 the slope has to become minus 40 dB per decade. See now here this is 25 radian per second frequency. We are coming down by 40 dB now. Just a minute. You can see I'm coming down by 40 dB going by 1 decade. So this point and this point corresponds to the 2 points where I can join this and this point so that the slope happens to be minus 40 dB per decade. From this 25 I will join, I'll try to join this line till 250, but I'm stopping at 100 because at 100 radian per second I have one more pole. So this line which is there, which is the reference, but I'm darkening this till only 100 because at 100 the slope again changes. Let us see what happens at 100 because at 100 you have one more pole. The slope becomes minus 60 dB per decade. So you can see now. So this line which was there at, so this corresponds to 100 radian per second. At 100 the slope again comes down to 60 dB and it is 1 decade. Now we can see if I join this point and this point, it's a minus 40 dB per decade slope. So this way we can complete the magnitude plot of the transfer function.